Oh, thank you so much. Today we are going to discuss physics, paper 1. Remember to invite a friend. Remember to share the broadcast with the people in your contact list. Remember to subscribe to this channel and to share the link with friends. Let me also share. Thank you so much for those who are continuing to join. Like, subscribe, share. Let's grow together. Please invite a physics student. This is for everybody. Yes. So we can now begin. We can now begin. Yes. This is that we are going to revise tonight. Remember, our consultation line is here. This is the number that you can use to request for learning materials. You can also join our revision groups using the same number. Number 1, the question says that figure 1 shows the scale of a measuring instrument when measuring the thickness of an object. So this is the scale. Actually, there are 2 scales. The first thing to do is to name the instrument to which the scale belongs. And this is definitely a vernier calipers. These are vernier calipers. Yeah, because this is called the main scale. Find the reading instrument shown. So now there is the reading displayed here. We usually say that for you to get the reading displayed on a vernier calipers, you are supposed to examine the 2 scales. So the first thing, get the main scale reading. The main scale reading. And for you to identify the main scale reading, then you are supposed to look at the value which is to the left of the 0 of the vernier scale. So on the vernier scale, we got the 0 mark here. Therefore, we identify the mark on the main scale, which is to the left of the vernier scale. And this is going to be exactly 5 vernier calipers. So measurements will be put to 2. Know is that measurements from a vernier caliper more places and in centimeters should be in centimeters. There is what we call the vernier scale reading. The vernier scale reading. Now, for you to identify the vernier scale reading, you must look for the mark in the vernier scale which coincides with another one in the main scale. And so we have 0, 1, then 2. It is the second mark which is coinciding with another one. So we will say that the vernier scale reading multiplied by what we call the least count. The least count of 1 over 100. This is going to give us 0.02. 0.02 centimeters. So now going to be when you add the main scale reading plus the vernier scale reading, this is going to give us 5.02. We have said to 2 decimal places and 2 inflated balloons, number 2, are at the same level while suspended from 2 threads a short distance apart. Some air is blown gently between the balloons in a horizontal direction. State and explain the observation made. So if you blow Remember, these are light balloons. There is a balloon here. There is another one here. They have been suspended. Then you blow some air horizontally in between them. They are some distance apart. So what happens is that they are going to be, or they are going to obey what we call the Bernoulli's effect, which says that provided that a fluid is non-viscous, a fluid as a streamline flow, then we usually say that, and it's also incompressible, incompressible, non-viscous, and having a streamline flow, then an increase in its velocity leads to a corresponding decrease to the pressure that it exerts. That means the air between the balloons will be moving at a very high speed, and with such a speed, now the velocity will lead to decrease in pressure between the two balloons. And now the atmospheric pressure on the outside, pressure due to atmosphere now, is pressure due to atmosphere. Pressure due to atmosphere is going to push the balloons close to one another, because inside the balloons, there is a reduced pressure. There is reduced pressure. So that is exactly what shall happen. Let's look at number 3, which is a question from the turning effect of a force. A uniform wooden bar of 1 meter and mass 500 grams is pivoted at 40 centimeter mark as shown in the figure 2 below. So we got a figure here whereby the pivot is seen at the 40 centimeter mark. We are also seeing that there is a force F1 acting through the 20 centimeter mark. There is also another force of 100 newtons acting at the end, 100 centimeter mark. Calculate the value of F1 if the system is to be in equilibrium. So to be in equilibrium, we usually say that for a system in equilibrium, the sum of clockwise moments is usually equal to the sum of the anti-clockwise moments. Thank you so much for turning up. I can see people really following up, and this is great. Continue inviting friends. Remember to subscribe to this channel. Remember to share the link with your friends. Remember to invite friends. Remember to subscribe. This is your channel. This is what will turn around your grade. So thank you so much for turning up. From Nyaururu High, I can see you people. So thank you so much. Now, we usually say that for a system in equilibrium, according to the principle of moments, which is also called the law of lever, the principle of moments, which is also called the law of lever, says that for a system in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments. Allow me not to write that statement, but I'm going to put it down mathematically, whereby I will say that the sum of clockwise moments is equal to sum of anti-clockwise moments. This is for a system in equilibrium. And so we are supposed to identify the forces which are responsible for the anti-clockwise moments, and also the forces which are responsible for the clockwise moments. It's good also for people to note that whenever a uniform bar is balanced, such that the pivot is not at the center, then the weight of the bar must act through its geometrical center. And so this is what it means, that the weight of the bar, because we are given the mass, we can get the weight by taking mg. So a mass of 500 times a g of 10, but this one should be in SI units, so we divide by 1,000. You discover that this is 5 Newton. So the weight of this bar is 5 Newton, and the 5 Newton should be acting through the geometrical center. 5 Newton weight acting at the 50 centimeter mark, the geometrical center of this metal bar or wooden bar, that is. So now, the forces which are responsible of the clockwise moment are going to be the 5 Newton weight and also the 100 Newton weight, which is at the end. And so we say that, remember, moments of a force are given by force times the perpendicular distance from the point of application of the force. So I will say that the first force, which is giving us a clockwise moment, is the weight. So 5 times the distance from the turning point is going to be 10, because we have 40, which is the pivot distance. Then the force is acting at the 50 centimeter mark. The distance there is going to be exactly 10. So we will talk about 10 out of 100. Remember, we should work with SI units. Plus, I'm trying to convert the centimeters to meters, plus another force of 100 multiplied by a distance of from 100 centimeter mark all the way to the 40 centimeter mark, we're going to have 60 centimeters. We convert them, equals to the anti-clockwise moments are only due to force F1 times a distance of from the 20th centimeter mark to the 40th centimeter mark. That is the distance that we want, and it's going to be exactly 20. So a student should not confuse this. The 20 we are using here is not the 20 centimeter mark. The 20 we are using here is the 20 between where the force is acting and where it has been pivoted. So that is 40 minus 20 to give us 20. So I'm not just reading 20 directly. You should be careful with that interpretation. Okay, so this is going to be 0.5. Let me write it well. 0.5 plus, this is going to be exactly 60, equals to, this is going to be 0.2 F1. And so we can say that 0.2 F1 equivalent to, when we take 60 plus 0.5, we get a 60.5. And so we can remain with F1 by dividing through by 0.2. And this is going to give us exactly 302.5. This is a Newton. So that is the value of the force. I'm still recognizing you for turning up. Thank you, Mark B. That is a Machakos school. I've noted you. Emmanuel Springs Boys High School. Wonderful. That is from Kwakathoka. I know the school. I know your principal, Mr. Dixon. The letters are not clear. Just check on your network kindly. I can see somebody from Nyambaria Boys. That is wonderful. Naivasha I, Mark B again, Moi Forces Academy. Where are you getting the 10 from? Where are you getting the 10 from? I think I explained that. Mary Hill Girls, Thika, Kadhiani Girls. Thank you so much. Thank you, great people. Thank you, Nehemiah Mbulo. I can see you from Mark B from 4A. Let's continue. Let's continue with this paper. Somebody is asking where 10 is coming from. 10 is the distance between the 50 centimeter mark and where the pivot is. State 2 major defects of a simple cell. We're just stating them. This is a local action. And there is also depolarization. Polarization, sorry. Polarization is overcoming it. Polarization. Polarization. Those are the two defects of a simple cell. Okay, number 5, a calculation. A mercury barometer reads 760 millimeters of mercury at sea level and 700 millimeters of mercury at the top of a mountain. If the density of mercury is 13,600 kilograms per meter cubed, and the density of air is 1.3 kilograms per meter cubed, calculate the height of the mountain. Calculate the height of the mountain. Thank you, Nairobi School and Machako School. Okay, for us to calculate the height of a mountain, we are supposed to know that the pressure difference which is being experienced here is due to the height of the air column, which is between the top of the mountain and the base of the mountain. And we usually say, because we are measuring air pressure, let's consider this. Just consider this. This is the mountain top. This is the mountain bottom. So if we talk about the air column acting at the bottom, you find that from the atmosphere to the bottom of the mountain, we have a greater air column than at the top. So a barometer is supposed to record a greater pressure at the bottom of the mountain than at the top of the mountain. So the pressure difference now is being brought about by this column of air within the mountain, just within the mountain. The column of air there is the one which gives us the pressure difference. So the first thing we're going to determine is the pressure difference. Pressure difference between the top and the bottom. When we take 760, we subtract 700. Ladies and gentlemen, we are getting 60 millimeters of mercury. So a pressure of 60 millimeters of mercury is the one now, which is it is the air column responsible of this pressure difference now. So this pressure is equal to the pressure of the air column, whose height is equal to the height of the mountain given here. And so we shall convert this pressure now to pascals. That is the ISI unit of pressure, or we even convert it to Newton per meter squared, which is the same as a pascal, which is the same as a pascal. The same as a pascal. So we say that pressure is usually given by H density times H is the height or the column density, then times the gravity. And we will say that 60 millimeters of mercury, that is the height of mercury that is being supported. We can divide this by 1,000 to make it SI units. Because they are millimeters, we divide by 1,000 to get meters, multiplied by the density of the mercury, 13,600, then times G. This is supposed to be equal to pressure, or it is the pressure due to the air column. So we can use the air column now, which is unknown, multiplied by density of air 1.3, multiplied by G, which is 10. And so we can remain with H by dividing through by 13, because that will be 13H. So we divide through by 13. This is going to give 627.69 meters. This is the column of air whose pressure is equivalent to the pressure difference. And so it becomes the height of the mountain. It also becomes the height of the mountain. Let's look at number 6. Figure 3 below shows a piece of wood fitted into a copper pipe and a piece of paper wrapped tightly around the junction. Explain why the side of paper around wood burns first when flame is applied at the junction. So when you apply a flame at the junction, you discover that the side of paper where there is copper pipe, there is no burning. Okay, or even if there is burning, it happens later. But on the side where there is wood, burning happens first. We are going to explain this. The reason why it happens so is because wood is a poor conductor, and therefore heat is going to accumulate at that point. Remember, I'm explaining this as a serious student, you should be able to take down the explanations that I'm making. So I will repeat what I'm saying, that hood being a poor conductor will, the heat will not be dissipated to the other part. It will just act on one part. And that is why burning is going to take place. On the other side, copper is a good conductor, so it shall transmit the heat away, and you find that the heat being supplied at the junction is not accumulating at one point. It will be dissipated away. It will be conducted away. It will be transmitted away. Therefore, we shall have the paper burning on the side where there is wood. So that is what makes the side of the wood to burn. Let's look at number 7, a very good question from quantity of heat. 0.2 kg of copper at 80 degrees Celsius is put in a well-lugged brass calorimeter of mass 0.1 kg containing 0.16 kilograms of seawater, at 20 degrees Celsius. Calculate the final steady temperature of the mixture. Take heat capacity of copper to be 400 joules per kilogram per Kelvin. Take the specific heat capacity of brass to be 380 joules per kilogram per Kelvin. And also take the heat capacity of seawater to be 3,900 joules per kilogram per Kelvin. I must correcting something in this. It should be known that Kelvin is capital K, not a small letter K. So this should be capital. Please make sure you don't make the same mistake as the typist did. Okay, now we are supposed to work out this question. Whenever you find a question from the quantity of heat, a topic in Form 4, in Form 3 physics, which is very simple, it should be known that you are first of all supposed to analyze the question, and you tell yourself that for it to be gained somewhere, it must be lost somewhere else. And the greatest assumption in this topic is that there is no heat loss to the surrounding. The greatest assumption that we make in this topic is that there isn't heat loss to the surrounding. Now that there is no heat loss to the surrounding, we should look at the material which is at a greater temperature. That one possesses some greater heat. So heat will be flowing from the material which is at a higher temperature to the materials, or to the material at a lower temperature. And when you look at our case here, there is copper at 80, then there is brass calorimeter and water, which are at 20. And so we can say that the heat lost by copper is equal to the heat gained by the calorimeter and the water inside the calorimeter. So we shall say that, remember, we are having the specific heat capacity is given. It is only the steady temperature which is not obtained. Therefore, we will say heat lost by the copper is equal to the heat gained on the other side now, gained by the calorimeter plus the heat gained by the water, or rather the seawater inside the calorimeter. So how do we get heat either gained or lost? The quantity of heat gained or lost is usually given by mass times specific heat capacity times the change in temperature. And so we are going to let the final temperature, in this case, to be capital T, just an abbreviation. That is not a standard abbreviation for final temperature, but for my case, I'm going to prefer it. Obanga School, thank you so much. Thank you so much. I can see Kalamba girls, Kambala girls. Thank you so much. Molo Academy schools represented. The Machaco School. Thank you so much, boys from our school. Loreto High School, Limuru. Thank you so much, our girls from Limuru. So let's continue. I can even see Chuka girls around. Kcse School. Wow. This is great. This is a great. This is a great. So thank you so much. We can continue with our revision. I'm going to recognize all of you. You can tag your school. You can tag your physics teacher. Invite more friends. Invite more friends. Tomorrow we'll be discussing mathematics paper 2, section 2. And I expect a bigger turn up than this. Though this is really amazing. This is amazing. Nyamangwa boys, wow, that's great. It is dissipated. Somebody is asking, what is being dissipated? Dissipated is transmitted away. Transmitted away. Thank you. So now we can express now and say that for the copper calorimeter, or for the copper material, sorry, we shall have a mass of 0.2 times, it is copper, so 400 is the specific heat capacity, times change in temperature. The change in temperature is from 80 to the unknown final temperature. So from 80 to T, you can write 80 minus the final temperature, which is not known. This is equal to, on the other side now, we can begin with a calorimeter of mass 0.1 multiplied by, it's made of brass. So brass is having a specific heat capacity of 380 times change in temperature. Now for the calorimeter, we are raising. The heat is raising, and it's raising from 20 to a certain final, which is not known. We have let it to be T. So we will use now T, the final temperature, minus the initial temperature that we add of 20, plus heat gained by seawater. Seawater is having a mass of 0.16 times specific heat capacity 3900 times T minus 20. Now we can find the value of T, because this is just a normal linear equation. When you multiply 0.2 and 400 times 80, you are going to get 6400. Then minus 80T. Yeah, minus 80T. This is equal to 0.1 by 380, we get 38T, minus 0.1 by 380 times negative 20. And that should give us exactly, let me get the value there. That should give us exactly 760. 760. Then we continue adding. When we take 0.16 times 3900 times T, that is going to give us 624T. 624T. Then we subtract 0.16 by 3900 times negative 20. That is going to give us exactly 12,480. 12,480. So with this, we can now group like terms together. We can group like terms together. We group like terms together. Remember, this should be 624T, sorry, not 62, 624T. 624T. Yeah, that way. We group like terms together. So we need to take 6400, we add 760, and we also add 12,480. That will give us 19,640 equals to, now we take 624T, we add 38T, and we also add 80, because it is negative at the left hand side. So it becomes also positive, 742 T. So for us to get the value of T, We divide it through by 742, and we are getting a value equivalent to 26.47 degrees Celsius. 0.47 degrees Celsius. Esa boys, Moiforces Academy, Mr. Mwoki. Wow, that's great. I send greetings to your physics teachers. Thank you so much. Thank you so much. Thank you so much. Let me upload the screen once more. Sorry for the interruption. Bahati Girls, Molo Academy. This is great. This is great. This is great. Mr. Onami McB. Wow, this is wonderful. Thank you so much, guys. Thank you so much, Madam Lillian. I send greetings to your respective physics teachers. Let's look at number 8. Figure 4 shows a liquid being siphoned from a beaker to another. Indicate on the diagram the direction of the flow of the liquid. So the liquid will be flowing from up there so I can use a direction like that one to show the flow. And we usually say that as long as there is a greater pressure on the one below, then we are going to have the flow continuing. We also asked to explain what would happen to the flow of the system if it was put in a vacuum. And I will say confidently that the flow continues. The flow continues. As long as you follow the same procedure of ensuring that before you insert in the container, as long as you ensure that the tube is filled with the liquid, then the flow is just going to continue. The flow shall continue. There is a very good explanation of this. A very good explanation of this in KLB Form 1 physics. Just check. We are told that a siphon can operate in a vacuum. A siphon can operate in a vacuum. To understand this, consider a chain or thick rope coiled into a bucket raised above the ground, and one end of it is over a pulley. See the figure here. The loose end air, when it is below the bucket, will have a net weight on it. This net weight resulting from the pull of gravity pulls down the chain completely out of the bucket. So as long as there is a net weight here, remember this rope is below the bucket. So the weight here, we are calling it the net weight. The net weight. So we are saying exactly at this level, there might not be movement of the rope. But as long as it is extended below the level of the bucket, then the rope is going to roll itself out of the bucket until it is completely not in the bucket. And so we are saying that the same happens to the siphon. The water will continue flowing out, or whatever liquid it is. State Hooke's law. It should be known that laws and principles must be stated exactly as they are Laws and principles must be stated exactly as they are. Exactly as they are. Bitini Girls, Mr. Albert. Wow, thank you. Mr. Kimuyu, physics teacher. Wow, this is great. Mr. Mboga from Nyambaria. Wonderful. So we are talking about the Hooke's law. The Hooke's law. Laws and principles must be stated exactly as they are. You are not supposed to paraphrase. You are not supposed to state it using your own words. You are not supposed to change meaning whenever you are putting down. Whenever you are putting down a law. Whenever you are putting down a law. I know the number of people who are following here are those who take physics, but kindly I want to request you to invite people tomorrow because it will be mathematics, and mathematics is compulsory. State Hooke's law. Should be known that Hooke's law states that for a helical spring or any other elastic material, extension is directly proportional to the force causing the extension, provided elastic limit is not exceeded. I'll repeat. For a spring, for a helical spring or other elastic materials, extension is directly proportional to the stretching force, provided elastic limit is not exceeded. Provided elastic limit is not exceeded. Number 10, an oil drop of radius 0.35 millimeters when placed in water spreads out to form a circle of radius 35 centimeters. Using this information, part A, estimate the size of the oil molecule. I must tell you something very sensitive. Something very sensitive. Estimate the size means the diameter of the molecule, and also this can mean the thickness of the molecule. So those words can be used interchangeably. We can say diameter of the molecule, size of the molecule, or thickness of the molecule. Please be conversant with those words. Now, an oil drop, which is a perfect sphere, when it is let to spread, it spreads until it occupies a very big area, such that it's almost becoming flat due to the thickness, which is very small, with a very small thickness. But now the idea here is that the volume of the spherical drop is equal to the volume of the oil patch after it has spread. And so we will say it is spreading to occupy a cylindrical shape because it has a flat cross-section and a certain thickness. It has a flat cross-section which is circular and a certain thickness, and it was originally spherical. So we say that volume of the sphere equals to volume of the patch which is created. In other words, allow me say this. Just write this expression. Volume of the spherical drop equals to volume of the cylindrical patch which gets formed. For a sphere, we deal with 4/3 pi r cubed. And on the other side, we shall talk of a cross-section area which is circular, pi r squared. I'm using capital R because the circular patch formed will have a very big area and will have a greater radius now compared to the radius of the drop, multiplied by the height, or rather the size or the thickness. Actually, we can call it height. Yeah, pi r squared h because it is cylindrical. So how do we get this h now? How do we get this h? We have to get h by dividing through by pi r squared. So we need 4 out of 3 pi small r power 3 divided by pi r squared. Remember, at such a point now, pi can cancel out. Pi can cancel out. And after pi has cancelled out, now we can substitute now. 4 over 3 times a radius of 0.35 we raise to power 3. Then we shall divide all this by r squared. The other radius is in centimeters. So we can work with similar units by first of all converting 35 into millimeters. To convert 35 into millimeters, we multiply by 10. So it will be 35 times 10, which is 350 now squared. 350 squared. Let me work out this. 4 out of b multiplied by 0.35 cubed. Then we divide by 350 squared. This will give us exactly 4.67 times 10 power negative 7. These are going to be millimeters. But now we can be told to express our value in SI units, whereby we will be required to say 4.67 times 10 power. It is negative 7. So when we divide by 1,000, it will become negative 10 meters. So it can also be written in SI units as times 10 power negative 10 meters. The next part, which is part B, state any one assumption you made in your calculation. Okay, the assumption that we are making is that the drop spreads to form a patch, which is a 1 molecule thick. 1 molecule thick. So the patch, the oil patch, is 1 molecule thickness, or 1 molecule thick. It's 1 molecule thick. We are also assuming that the oil drop is a perfect sphere. The oil drop is assumed to be a perfect sphere. Remember to be here tomorrow for mathematics paper 2. Remember to be around. Let's look at section 2 now. Distinguish between inelastic and elastic collisions. This one I must write down now. When we are talking about inelastic collision, this is whereby bodies stick together, then they move. After collision, bodies move together. So we say when they move together, it is only linear momentum which is conserved, but kinetic energy is not. So elastic or inelastic collision, bodies stick together after collision, stick and move together, after collision. This is just a description of the type of collision. You should go ahead and give a scientific description whereby we say only linear momentum is conserved. But kinetic energy is not. Kinetic energy is not conserved during inelastic collisions. When we are talking about elastic collision, while elastic collision, bodies move separately after collision. Bodies move separately after collision. Bodies move separately after collision, and we are saying that both kinetic energy and linear momentum are conserved. Both kinetic energy and linear momentum are conserved. We can look at part 2, whereby we are told that a particle A of mass m moving with an initial velocity of u makes a head-on collision with another particle B of mass 2m, B being initially at rest. In terms of u, calculate the final velocity of A if the collision is perfectly inelastic. Perfectly inelastic means that they collide and move together after collision. And in this case, we are saying linear momentum is conserved. With linear momentum being conserved, then we say momentum before collision, is equal to momentum after collision. Momentum before collision equals to momentum after collision. Again, we should know that momentum is given by mass times the velocity of an object. So what is the total? Actually, it should be total momentum before collision equals to total momentum after collision, because linear momentum is being conserved totally. Linear momentum is being conserved. So how do we put this now? We say that particle A is having mass m. So mass times its original velocity, initial velocity, plus body m is having a mass 2m multiplied by initial velocity of 0. So the momentum for body B is 0 because it's mass times velocity. No matter how big mass can be, as long as the velocity is 0, the momentum has to become 0, because momentum is a derived quantity where you should multiply both mass and the velocity. Now, because they are in what we are calling perfectly inelastic, they are combining and becoming one body, then they move together. So we will have the mass now after collision m plus 2m multiplied by the common velocity, which is not known. So this is going to be mu plus 0 equals to 3m when we add m and 2m multiplied by the common velocity. And now we can remain with the common velocity by saying v is going to be, we take m u divided by 3m. That is how we remain with v. M can cancel, and we say that the value of v equals to be u divided by 3. So v equals to a third u, or 0.33, the value of u. So we have expressed the final velocity in terms of the initial velocity. Something that you must understand, we are told to calculate the final velocity of A. Because they are colliding and sticking together and moving together, the velocity of A is also the velocity of B. So the final velocity that we are calculating for both bodies is for A and also for B. is for A and also for B. Oh, thank you so much. Ngoto Boys is inside. Thank you so much, Benson Maundu. This is Ngoto Boys. Send greetings to Ngoto Boys, both the teachers and students. Invite more friends for mathematics tomorrow. Paper 2. Limuru girls, wonderful. This is great. Invite your friends from Limuru girls and send greetings to them. Say hi to the teachers. Tag friends here. Tag your friend. Tag your teacher. Let's continue learning physics. We continue part B. Part B. We are told that the diagram in figure 5 below shows a sphere moving in a viscous liquid. Moving in a viscous liquid. A viscous liquid is a liquid which has what? Friction. Because viscosity is a friction in fluids. Then we are told that it's in a tall measuring cylinder. Yeah, we have the sphere, we have the viscous liquid, we have the measuring cylinder, as you can see in the diagrams. Then the first thing is telling us to do what? Show on the diagram the forces acting on the sphere. The forces acting on the sphere, which are acting on it. The three forces are going to be, let me change my ink. First of all, there is its own weight, which is going downwards. Weight W going downwards. But now there is a upthrust. Remember, when an object is in a fluid, it experiences upthrust. So there is an upthrust acting upwards. The friction or the viscous drag, because it is inside a fluid, there will be viscous drag, frictional force due to the viscous liquid. So we shall have three forces: friction, which is against the motion; upthrust, also against the motion, that is they're going upwards. But now we have the weight of the body going downwards. Then we are told to sketch a graph showing the variation of velocity with the time in the figure 6 below. Show on the graph the terminal velocity, Vt, of this object. So we should know that the body moves with a varying acceleration, which means we're going to have it like this. Then at some point, it levels. At that point now, it has attained what we call terminal velocity. So if you move from this point now, the value of velocity here will be the terminal velocity. The terminal velocity. So learners should understand. Learners should understand this. Take it keenly. Learners should understand this. In case you plot it this way, let me show you something. In case you plot it this way, in case you plot your velocity, this is time in seconds. This is the velocity. In case you plot it this way, such that you want to have a straight line, then you curve this way. A graph almost like that one of the Hooke's law. You are going to get a zero because you mean that your acceleration is uniform. This means uniform acceleration. So you are going to get it wrong. It should be a curve showing that the acceleration is varying as the body goes down. The acceleration is varying as the body goes down. So it must be a varying acceleration. St. Francis Mangu present. This is great. This is great. So let everybody recognize their own school. Wow, this is wonderful. This is wonderful. This is wonderful. Wow, this is great. This is great. Okay. Number 12. This is a question which I've tried to show, but we are going to handle it the way it is. So we shall do the question at a point where it will allow us to do it. Sketch a block and tackle pulley system with 3 movable pulleys in the lower block and 2 fixed in the upper block. 2 fixed in the upper block. 2 fixed in the upper block. So we have a fixed pulleys and movable pulleys. So the 3 movable are in the lower and the 2 which are fixed are in the upper. So let me start with the 2 pulleys in the upper, then 3 in the lower. So I'm planning to draw a decent diagram. So the fixed ones are fixed here, and they are only 2. So we have 1 and 2. We have 1, 2. Then after this, we have on the other side now 3 movable ones. 1, 2, then 3. Remember, on the movable pulleys, this is where you will fix now. This is where you will fix the rope. There will be an hook there for the load. An hook for the load. So the way we wrap our rope now, the way we are going to fix our rope is what will determine everything. So we're going to move from this point. I'm now fixing the rope. Continue flowing. Then finally you'll be here. Yes. Mr. James Udror, thank you so much, physics teachers. Thank you so much, physics teachers, for presenting these good students. Home School, Miraria, represented. Wow, this is great. Nairobi School in the house, Kagumo High, Girls Nairobi, Molo Academy Schools. Wow, St. Charles Luanka. I think this is great, young men. This is great, ladies and gentlemen. Continue learning physics. Continue learning physics. Okay. Now this is how we draw it. And the other thing we are taught to find is to find the velocity ratio. We're supposed to know that a velocity ratio is the number of ropes which are supporting the load. If we were to fix a load, it would be somewhere here. If we were to fix a load, it would be somewhere there. Therefore, the load is supported by 1 to go upwards. It's also intended to go upwards. So I believe we are together in that. We can continue pursuing this paper. We can continue pursuing the paper. We can continue pursuing the paper. Yeah. An effort of 450 newtons is used to raise a load of 2,700 Newton. Determine part 1, mechanical advantage. should be known that a mechanical advantage of a machine is the ratio of the load to effort. So a load of 2700 and an effort of 450, they are giving us exactly 6. Then we also proceed efficiency of the pulley system. Efficiency is usually given by mechanical advantage out of velocity ratio times 100. So we need a velocity ratio and a mechanical advantage of both 6 times 100, giving us an efficiency of 100. Though it's not practically possible, to have a pulley with 100% efficiency. The question is allowing us to get such an efficiency. Kcse girls. Thank you, people. Thank you, people. Thank you, ladies and gentlemen. If all the wasted energy, now let us look at this question now. If all the wasted energy is used to raise the lower block and the frictional force between the pulleys and the moving parts is 3.6 Newton, determine the weight of the lower block. I would like to register my apologies because of such a question. One, you are supposed to understand that when the efficiency of a machine is exactly 80%, is exactly 100%, there is no energy which is wasted. Again, if they were to state energy, I think there was an issue in typing of this question. If they were to state energy, then energy cannot be given in newtons. It can either be Newton meter or in joules. So I cannot take 3.9 newtons as energy. And also, I cannot understand energy being wasted, yet we have calculated an efficiency of 100%. So there is an issue with the setting, maybe the choice of values or something. So even the part 4 now will become a bit controversial. Somebody is saying that velocity ratio is 5. That is not true. The part of the rope where you are going to apply the effort is also facing upwards. And we said if it faces pardon the working. People are telling me to pardon my working on the calculation of VR. VR is the number of ropes supporting the load. And as you can see, there is 1, 2, 3, 4, 5, and this one is treated to be the 6th because it is also facing upwards. The direction is upward. If, for example, we had this case, let me make it simpler for you. If we had a setting like this, I must make you understand. That is why I'm around. No, that is not what I want. What I want is this way. Yeah, this way. Let's assume that it was this way now. You see that effort is facing downwards, yet if we add a load here, it would be intended to go up. And so we will say that in this case, the velocity ratio is simply the number of ropes which are supporting the load. So we have this one, this one, this one, this one. So VR would be 4 in this case. But in the previous case, the question that we are handling, you can see that the part of the rope onto which you shall apply your effort is facing upwards, and therefore it will be treated as one of the ropes which are supporting the load, as one of the ropes which are supporting the load. And so we are saying velocity ratio is exactly 6. So I believe we are together in that. We are winding up. We are winding up. Kadiani girls, thank you so much for turning up. Yeah, so allow me now to go to this part C, which says James applied a force of 400 Newton in pushing a stationary wall. If it took 1 hour to push the wall, calculate the power developed. Remember, we said that power equals to the rate of energy conversion or work per unit time. In this case, the work done is going to be force times distance. This person is pushing a stationary wall, therefore there is no distance moved, and so we shall say work becomes 0. If work is 0, then if work equals to 0 because of force times 0 distance, 0 divided by anything, it just becomes 0. So the power is 0. The power is 0 watts or 0 joules per second. So there is no power developed. In other words, there is no work done because there is no distance moved. Scientifically, we say work is only done when a distance is moved. Number 13. Remember, we are winding up. State the pressure law. The pressure law of an ideal gas states that for a fixed mass of a gas, you should be taking down dictation. For a fixed mass of a gas, the pressure is directly proportional to the absolute temperature, provided that the volume is kept constant. Provided the volume is kept constant. Explain how a gas exerts pressure. A gas exerts pressure because, or in this way, the collisions or the movements, the random movement, the particles. We can start with the particles of gas. The particles of the gas are in constant random motion. Constant random motion. And when they are in constant random motion, remember that is according to, the idea is even from particulate nature of matter. So the particles of the gas are in constant random motion, colliding, making them colliding with the walls of the container, hence exerting pressure. So pressure is squarely due to collision of the gas particles with the walls of the container where the gas is. There is a figure here which shows a setup used to verify the pressure law. So we can see there is a beaker containing a thermometer, hot water. There is a dry air in a glass flask. Then we can see a Bourdon gauge. It serves the same purpose as a pressure gauge. Serves the same purpose as a pressure gauge. The work is to record pressure. So when you look at this question, we are told that the first thing is to state two measurements that may be taken in the experiment. When you look at the apparatus there are only two apparatus from which some quantities can be read. There is a thermometer, which means temperature can be read. Temperature can be read. There is a Borden gauge, which means again pressure can be recorded. It's good to know that we are simply comparing temperature and pressure. Explain how the measurements in one above may be used to verify, how they may be used to verify the pressure law, how they may be used to verify the pressure law. To verify the pressure law, now you need to, okay, let me describe a simple procedure, just a simple procedure. Know that the first thing you should do is you record initial temperature and pressure. Record initial temperature and pressure. Then after that, after you record initial temperature and pressure, we can talk about after some intervals now. After some intervals, record several values of temperature. Several values of temperature with the corresponding values. With the corresponding values of pressure. With the corresponding values of pressure. So you record at some given interval. So you tabulate. Actually, you tabulate several values. Then once you do that, you plot pressure against temperature. Plot pressure against temperature. Let me post again. Sorry for the continued interruptions here. Thank you for remaining. Tomorrow it will be mathematics. Tomorrow it will be math. You will invite in the villages and in the cities where you come from. Plot pressure against temperature. So it has to be known that when you plot pressure against temperature now, a graph or a straight line shows that pressure is directly proportional to temperature. Hence, the pressure law. Hence, the pressure law is verified. Hence, the pressure law verified. Hence, the pressure law is verified. We can mention something about uniform circular motion. Continue liking our videos. Continue subscribing to this platform. Continue inviting friends. Continue learning with shifting grades. A body moving in a circular path at constant speed. Consider that the word there is constant speed. At constant speed is said to be accelerating. Explain. Remember, we say that acceleration is the change in velocity with change in time. And so we are saying, even though the speed is common, remember a circular motion, a circular path is this way. In case this body is cut from the circular path, it will move following a tangent. at that point where it is cut. So the body will move in that using a certain velocity. If the body is at this point and you cut it from the path, it's going to move at a certain velocity following a path which is equal to the tangent at that particular point. And so we can say that even though the speed is the same, the fact that the direction is changing, it makes the velocity to be different, because we say velocity is speed in a specified direction. So when direction changes, even if the quantity of speed remains the same, the velocity is said to have changed. So due to change in direction, due to change, this is the argument that you should give your teacher now when you go back to class. Due to change in the direction, of the body, actually instantaneously, due to the instantaneous change in direction of the body, due to instantaneous change in the direction of the body with time, the velocity is also changing, and hence the body is said to be accelerating. The body is said to be accelerating. The body is said to be accelerating. Let us look at part B now. The diagram below shows the mass M, which is rotated in a vertical circle. The speed of the mass is gradually increased until the string breaks. The string breaks when the mass is at its lowest position A and at a speed of 30 meters per second. Point A is 5 meters above the ground. Therefore, we have point A here, where the body breaks, the lowest point of the circular path. So once it breaks, we said in the earlier argument that the body will trace a tangent at that point. But the body cannot continue flying forever. At some given point, the body has to fall down. So how do we account for that? There is the vertical height, which we are saying it is 5 meters from the ground. Then we also say that assuming that this body was falling freely, we usually say that the time for free fall is equivalent to the time of flight. What do I mean? In case from a certain height here, let me draw that demonstration. Let me draw that demonstration. In case there is a certain height here, then there is the horizontal ground. We usually say that if a body is falling from this height h, the time it will take will be equal to the time in case the body is thrown to a further distance. The body will take the same time. And so we will say that there is a time t. There is a time t, which is that we don't know, and we can calculate that time first. The time the mass takes to reach the ground after breaking off. So we are going to say height is usually given by half gt squared. So the height of 5 is given by half times a gravity of 10 multiplied by 10 squared. This equals to 5t squared. That's after dividing by 2. Then we can divide through to get 1 equals to t squared. And the value of t becomes exactly 1 second. Therefore, this body will take 10 seconds to reach the ground. It will take 10 seconds to reach the ground. We are also calculating the horizontal ground the mass travels before it strikes the ground. So what you're supposed to know is that the horizontal distance covered is called range, capital R, and is given by u multiplied by t. U is the initial velocity of this body. So it breaks with a velocity of 30 meters per second, according to the instructions here, at a speed of 30 meters per second. Therefore, we shall say a speed of 30 times time 1 second give us a distance of 30 meters. For the range will be exactly 30 meters. Okay. We are also told to calculate the vertical velocity with which the mass strikes the ground. So as it comes to the ground, it gains some velocity, and we shall say that the body is converting its potential energy, which is gravitational potential energy, is converted to kinetic energy towards the ground, is converted to kinetic energy as the body approaches the ground. And so we can say that gravitational potential energy is given by mass of a body times the gravity multiplied by the height equals to kinetic energy, which is half mv squared. Half mv squared. So now with this case, mass is appearing on both sides, and we can it can simplify out. So 10, which is the gravity, times a height of 5 equals to half multiplied by v squared. And at this point now we can multiply by 2 through, so that we get 100 equals to v squared. So v equals to, we obtain the root 10 meters per second. So the body is going to land at the ground with a velocity of 10 meters per second. Part C, the graph below was obtained when an experiment to investigate the variation of the centripetal force F with radius R of the circle on which a body rotates was performed. So the graph is already plotted for us. Ours is to analyze it. We have force in Newton, we have radius in meters. We can see a straight line. Then we are told that from the graph, determine the angular velocity of the body, given that m equals to 100 grams. So what we're supposed to do in this case is to know that from such a graph, because force has been, remember there is an equation here actually, that is what we are going to use. We shall analyze this equation in reference to the graph. So F equals to mass times angular velocity squared multiplied by radius plus c. Compare this with the general equation of a straight line, which is y equals to mx plus c. So the coefficient of x, which is m, gives us the slope, and the vertical intercept is c. Therefore, in this case, now we'll say that our mass times angular velocity squared is the coefficient of whatever is in the x-axis. On the x-axis, we have r. On the y-axis, we have f. And so the coefficient of r becomes our slope. So slope in physics is gradient in mathematics. So slope is given by mass multiplied by omega squared. And so we can say the value of slope S can be determined first. So we go to our graph now and we calculate the slope. We must identify some coordinates which are lying on the line for us to calculate the slope. So we can have a 1 point or 0.15, a coordinate like a 0.15, 0.15, and 0. This is going to be 0.26. That's the coordinate. Another coordinate can even be read from a point like this. At this point, we can have a point like a 0.03 and 0.1. That's a coordinate. So with these two coordinates, we can determine our slope. So we need to get a change in y. So 0.1 minus 0.6 divided by 0.03 minus 0.15. So this is going to be negative 0.16 divided by negative 0.12. This will give us exactly 1.33. So the slope is exactly 1.33. 1.33. So if this is the slope, now we can come to our equation and say the value of the slope 1.33 equals to mass, and the mass of the object is known. So the mass of the object is already given here as 100 grams. So we can use SI units. 100 grams we divide by 1,000 to get 0.1 kilogram times the known omega squared. So to remain with omega squared, we divide through by 0.1. This becomes 13.33, and we can take square root now to get our omega is exactly 3.65. Being omega, or rather angular velocity, then we can write it as radians per second. So the units of omega is radian per second squared. Finally, we have number 15. We are winding up now. The diagram in the figure below shows a block of wood floating to a depth of 0.18 in water. The density of water is 1,000 kilograms per meter cubed. 1,000 kilograms per meter cubed. So the first thing we are determining is the mass of the wood. We are going to apply what we call the law of flotation. The law of flotation says that a floating object displaces its own weight on the fluid in which it floats. A floating object displaces its own weight. Therefore, the weight of the fluid, which will be displaced by this block, will be equal to its own weight because the block is floating. So let's get that first. So we can determine the weight of water displaced by saying that a volume of water displaced equals to length times width times height. 0.5 times 0.3 times the height, which is inside water, 0.18. This is going to give us a 0.027 meters cubed. This is the volume of water displaced. And this means we can get a weight of water displaced. So the weight of water displaced will be given by, when we take volume times the density of water, we shall obtain the mass. So mass times G will give us now the weight. So weight of water displaced equals to 0.027 times density 1,000 times G, which is 10. And this is going to be 270 Newton. So 270 Newton is the weight of water displaced. That means if that is the weight of then weight of wood is also equal to 70 Newton. which means with weight, for us to get mass, we just need to divide by G, 270 over 10, and we get 27 kilogram. That is the mass of the wood. Density of the wood. For us to get density, we need mass out of volume. So we have to calculate volume first of the wood, whereby we need now the total dimensions. 0.5, 0.3, 0.2. 0.5 by 0.3 by 0.2. And this is exactly 0.03 meters cubed. So with this volume, now we can get our density, a mass of 27 out of a volume of 0.03, and this will give us exactly 900 kilogram per meter cubed. 9,000 kilogram per meter cubed. Finally, there is a question here which is saying, determine the number of frogs, each of mass 500 grams, which will make the block of wood to be just submerged if they sit on the block. So we are supposed to know that there is a height of 0.18 for this block, which is already inside, and the total height of the block is 0.2. So the remaining height is just 0.02. So we ask ourselves that a height of 0.18 meters of the block is inside the water because of the 28 kilograms of the block itself. What about the remaining 0.02 meters? What about this? It has to be 27 times 0.02 divided by 0.18. This will require exactly 3 kilogram. If it requires 3 kilogram, then we are going to tell ourselves one thing, that the frogs are weighing 500 grams. So with 500 grams now, how many frogs are needed to give us a 3 kg? 3 kg can be converted also to grams. That will be 3,000 grams divided by 500 grams, and we exactly need 6 of them. It's good to have your answers in SI units. So 6 frogs are required. Remember to subscribe to this channel. Remember to share the link with your friends. Let us meet tomorrow for mathematics paper 2. Thank you so much for turning up tonight.